Hey there, folks. Let's do some more homework. We'll do the rest of this. Hopefully, get it taped without any issues. And then I think we pick up with number 17 tomorrow and finish up 5.1. Move on into 5.2. So let's start with problem 10. Problem 10 is talking about the restriction of a relation to a subset of the domain space of the first space. I shouldn't call it domain. But all you do is you take things that are in the cross product of the subset and your second set that are actually related. So it's actually intersection of your relation with C cross B. So if this is our relation, here's the A part. If this is our relation on 1, 2, 3, 4, 5 going into the natural numbers, then find the restriction of R onto C, where C is 2 and 3 and 4. So in that case, R restricted to C, we take everything that starts with a 2 or 3 or 4. So that's 2, 3, 2, 1, 3, 5, 4, 4, and that's it. With C being 1, 3, and 5, we'll take everything out of R that starts with 1. So 1, 3, and 3, 5, and 5, 4, and 5, 2. And then with C equal to 5, we just take those last two. 5, 4, and 5, 2. Okay, very good. If S is the relation on the real numbers defined by y equals x squared, compare the graphs. Well, if you graph a parabola, I think you guys are familiar with this graph. Kind of looks like so on that side and like so on the other. And I'm not taking the time to put numbers on there, but you know what a parabola looks like. If you restrict this to just the non-negative domain, then it looks more like this. And you don't draw the other side, right? Okay. If LEQ is the relation on 1, 2, 3, 4, 5 defined by less than or equal to, then list the things in this relation, which is all ordered pairs that you can have with those things in the first and second coordinates, that fit into that have 1, 2, or 3 in the first coordinate. So there's actually several of these things in the first one. We got 1 less than or equal to 1, and 1 less than or equal to 2, and 3, and 4, and 5, and 6, and then 2 is what, I'm sorry, there is no 6. What's wrong with it? So let's make this 2, and I'll leave the 6 there, and 2 and 5, and 2 and 4, and there's no 6. There's no 6 there at all. How about I just mark that one out? Excuse me. 2 and 5, 2 and 4. I'll get it. 2 and 3, 2 and 2. And then with 3, we've got 3 and 3, 3 and 4, and 3 and 5. Okay, all those things. I don't know why I was thinking 6. Is there 6 in another problem? No, never mind. With 2 and 4, it would be just, let's see, 2 is less than 2, less than or equal to 2. 2 is less than or equal to 3. 2 is less than or equal to 4. That's a 3. 2 is less than or equal to 5. 4 is less than or equal to 4, and 4 is less than or equal to 5. And that's it. And then with 6, there's only one thing. 6 is less than Is there supposed to be a 6? I think there was a 6. Okay, there was a 6. Okay, my bad. I thought something. I remember doing a 6 here. So with a 6, I got to put some extra points in. 1 through 6. I'll put that 2, 6 back in there. I got to have a 3 to 6 as well. And here, let's see, I got to have a 2 to 6 and a 4 to 6. I thought there was a 6 in there. Okay. There we go. Sorry, a little messy, but we still got it. Okay. So there's 10. '11 has us looking at the composition of relations. That's where we have something that goes from A to B, and then B goes, the second relation goes B to C. Then we say that second one is composed with the first one. What we do is we take ordered pairs that are connected by something in that connector set, that B set. Okay. So if we look at R6 composed with R4, first we look at R4 and say, okay, well, the ordered pairs here start with a 2. So the ordered pairs, if you look at this, the ordered pairs come from the first one. The first coordinate comes from the first one. And then if it's connected to something second, then we get the second coordinate out of the second set. So we got to start with 2 and then go to 1. And then when we look at 6, 1 is connected to both 1 and 2. So we've got 2, 1, 2, 1, 1, 1. And then 2, 1, 1, 2. So 2, 2. Okay? Which I think is then R11, right? R sub 11. Now, when you change the order, first now we start with R6. So everything here starts with a 1. And it's connected to both 1 and 2. So 1, 1. There's no 1 over here so to connect to, so we don't do that. We've got 1 goes to 2 and 2 goes to 1, so that's 1, 1. And we're done, and that's actually R2. R sub 2. Okay? We did this with diagrams a bit in class, right? Kind of drawing the pictures of how these things got connected. Okay? So if we do R4 to R4, well, we start with a 2, which goes to the 1, and then we go to this set and look for a 1 to connect it, but there isn't one, so this is just an empty set. With R6, we start with a 1 and go to a 1, and then 1 in the second R6 is connected to both 1 and 2. So we get both of those points. We get 1, 1, and 1, 2. And then 1's connected to 2 right here, but there is no starting 2, so that's it, we're done. So that is actually in that R6. Yeah. Okay. R16 is the entire Cartesian product. R7 has these two elements in it, so if we do a composition of this, with R7 we've got 1 mapped to 1, and then here 1's mapped to everything. So we get 1, 1, 1, 2, 1, 3. And then we've got 2. So our ordered pairs now will start with 2. And that is mapped to 1, which gets mapped to everything. So 2, 1, 2, 2, 2, 3. And let's see. Oh, there are no 3s in this set. What's wrong with me? Gosh, I'm messing up. There's just 1s and 2s. So forget this and forget that. Sorry about that. Right. Just 1s and 2s, my bad. Losing my mind. Okay. So now we need to, before we do this, we need to think really about what's happening here, but we've got that. Right? We've got this up here. So then we look at R11 and say, okay, everything here starts with a 2, and then 2 gets mapped to both 1 and 2. So 2 being mapped to a 1, and then I've got a couple things here that 1 is mapped to. So 2, 1, 2, 1 to 2. Okay. And then 2 is also mapped to 2, which is also mapped to 1 and 2. So 2, oh, which is the same stuff. Right. 2, yeah, that is the same stuff. Never mind, sorry. Okay, which I think is R11. Right. Now let's take it in different order. R11 is this, so everything starts with a 2, and it's mapped to 1 and 2. And then we go to R7, here's R7. So starting with 2, and then everything in 7 gets mapped to 1. So everything here starts with a 2. You go to 1, you go to 1. If you go to 2, you go to 1. So we just end up with 2, 1. And that's R4. And so we've got this, everything here, this is going right there, right? And then 16 will give us everything that 1 is mapped to. So we start with a 2, and then 1 is going to be mapped to both 1 and 2. Right, 2 to 1, and then 1 in R16, which is the whole deal, the Cartesian product, 1 will get mapped to both 1 and 2. So 2 is the first coordinate, and 1 and 2 are the second, and that's actually R11. Okay? All right. So that's 11. Hopefully you're kind of following how that composition stuff goes. All right. Now we want to show that for any relation R, S, and T on a set A, so we never have to worry about what set we're in. We're always working in A. That it doesn't matter whether you compose the first 2. If you have 3 things being composed, it doesn't matter if how you group them. In other words, it's associative on composition. You can either group the first 2 and compose with T, or you can take R and compose with the last 2. Okay? And the way I think of doing this is really with set inclusion. This is set, that's a set, they're both sets of ordered pairs. Let's show that they're equal by showing that one is a subset of the other. So here's my proof. And I think was it Marcus maybe did this with set builder notation in class, but I'm going to go ahead and kind of do it the traditional way. So let's take a element of the relation over here. I'll call it AD. Let that be in R composed with S, quantity composed with T. Okay? Then there exists a B, okay, in A. The reason I say this is this starts in A. It starts with the little a in A, goes through T, and then the D comes out of this business. So there's got to be a B that connects AB and BD. Okay, so there exists a B in A such that, now let's think about it, AB is in T, and then BD is in R composed with S. Okay, that gives me the B is the connector that gets me from A to D. But there's a connector that gets me from B to D as well, because these are composed. Then there exists a C in A such that B, C is in S and C, D is in R. Okay? So what does that tell me? Well, look what I'm trying to build over here. S composed with T. Let's look at something in T that's connected with S. I go from A to B in T, and then in S I go from B to C. Then AC is in S composed with T. It's composed with. Okay. And then when I look at R, C is my connector from AD. Then A, it goes to C, and then ends up at D. That's in R composed with S composed with T. Thus, I've proven that that left-hand side is a subset of the right-hand side. Okay, now let's go the other way. Now, let AD be an element of the right-hand side, R of the quantity S of T. Okay, then A comes out of S of T. There's some connector there. I'll call it, doesn't matter if I call it B or C or whatever it is. How about C? In a set A, such that now the AC has to come out of this. S composed with T. And then C is the connector to D. And CD is an element of R. Okay? But this is a composition as well, so then there exists a B in A that will connect these two together. So AB is in T and BC is in S. Alright, but let's see what we're trying to build here. Let's start with S and move to R. So here's S, starts with B, connected with the C, goes to D. Then B, D is an element of R composed with S. You start with the S, B, it's connected with the C, and then you end up with the D. And where's T? Starting with T, I've got A goes to B, and then B is my connector to D. So AD then is, and I've got my R of S right there, because that's where I end up, and then I start with T. Okay? Thus, we've shown that R composed with S of T is a subset of R composed with S, quantity composed with T. So since I've got them one subset, this subset of this subset of that, therefore, the big finish for this, right? Remember the big finish. Therefore, the sets are equal, and we are done. Okay. So that's one of the first kind of set things we've done, really. Okay, let's talk about Rn can be in 1 through 16 here. Okay, but R1 is the empty set. Okay, I should have written that down somewhere. Let's see, R1 is the empty set. So empty set doesn't allow any connections, right? No matter what we got in Rn, whatever's connected to, there's no front end connections to get us any back end connections. So this is just empty set as well. And there's also no starting connections, so empty set either way. Okay. R8 is the identity relation. It maps 1 to 1 and 2 to 2. Right. There we go. So this is just going to give you what you put into it, R8, right? Oh, I'm sorry, Rn, excuse me. Rn and Rn. Because you're just doing a straight line across, if you think about the diagram. And then with Rn, now this is the entire Cartesian product. So whatever first coordinates you have, this is the set of AB such that A is a first coordinate, or it's in the domain of Rn, and B equals 1 and 2. Right? Because once you map to whatever that is, it maps to both 1 and 2 over here. And then here you have every possible starting coordinate. So I'll say AB again. But then whether it gets to a second coordinate depends upon whether or not that second coordinate is in Rn, where B is a second coordinate of Rn, and now A is 1 and 2. Okay. And then 14 says, okay, suppose R is a relation on a given alternate definition of transitivity using composition. Well, if you remember what happens here, R will take A to B, and then we'll have B related to some C. What we're saying here is that I should be able to go straight from A to B. Well, composition takes us from the ordered pairs in one connected to the ordered pairs in another and takes us straight across. So what we can say here is we have transitivity of R if and only if when I do the composition that falls inside R. And it's a subset because you could have D standing out here connected to E, right, by R. But it's never tested, it never figured, it's not connected to anything else, so it never figures into the calculation of transitivity. The relation here would take us from A to B. B is only connected to C, so it only takes us there. Okay, but this other stuff wouldn't be a part of the composition. You know, D goes to E, but E is not mapped to anything, so it doesn't show up. Okay, and I think we got just one more with a few little parts. Here they start to talk about the inverse relation of R. And this is kind of interesting because in the past when we've used that notation, it's been assumed, you know, we were dealing with functions. And when we use that a lot of times with functions, we say, okay, well, the only time we have an inverse is if this function has special properties, which we talked about last time, one-to-one, one-to-one, and then onto is something we assume we limit the range when we deal with, you know, in algebra. But here, you can have an inverse relation that's not going to match up to things like functions and stuff like that, right? All we do is we just turn all the coordinates around. Okay, we take the b comma a's such that AB was in R. So it's actually quite easy in many of these cases to find the inverses. If they list it out, just relist it with the X and Y switch, or not X and Y, sorry, the first and second coordinate switch. 5, 1, 5, 3, and 3, 5. Okay. Here, our inverse on naturals defined by X inverse R of Y if, and we do the same thing, just if Y is less than X squared. Change out the roles. So here with T inverse 0, 0, 7, 0, 0, 7, 7, 7, and 4, 4. And if you'll notice, that's exactly the same set. Here's a relation that is its own inverse. Okay. Naturally, it's very symmetric, right? Think about inverses. What we mean by symmetric is symmetric across that diagonal line. Well, that's exactly what we do with functions, right? We take the x and the y and we swap them over there. Okay. Same thing here. U inverse would be defined by x u inverse y if and only if yx equals, greater than 0, which is exactly what we started with. So this is actually the same as it's its own inverse. And actually the same thing happens here, right? P inverse would just be x P inverse of y if and only if the greatest common divisor of y and x is 1. Well, it doesn't matter what order you write those in. Okay, so again, that's its own inverse. And then B, it's an open-ended question. They don't actually ask us to necessarily describe what these are. I think they're just wanting us to figure out that it's not what you think it might be. Typically, you know, when we do this in algebra, when we look at a function composed with its inverse and an inverse composed with its function, we get the identity, right? And so if R is from A to B, and R inverse then is from B to A, what you would expect maybe to happen is that R composed with R inverse would give you all the ordered pairs in the domain. Let's see, where do we land? We land in R, which is B. We would expect to get things of the form BB, right? We start with things in the set B, go to A, and then this. for all B in the set B. But that's not necessary, and then vice versa, we'd expect to see R inverse starting, I did it backwards. R inverse starts with A, I did. I'll just fix it like this. There we go. R inverse starts with A, goes to B, and then ends up in A. So this would be all AA's, where A is an element of A. However, that's not what happens. Let's look at an example. This, by the way, is wrong. We'll do R and R inverse. So we're actually looking at R inverse opposed with R, because we start with R, right? Now let's let our set be, I don't know, A, B, C, D, and then maybe 1, 2, 3, and then back to A, B, C, D. Now what should happen, I should get a clean walkover from A to A, right? So maybe A goes to 1. And then B goes to 2. But B also goes to 3. And maybe C goes to 3. I'm sorry, D goes to 3, and we'll leave C alone. Well, reverse all these. So 1 does go to A. 2 goes to B. But then 3 goes to B. And 3 goes to D. Right. See what I did? Just reversing the direction of all these arrows. Okay. So what do I end up with in here? Well, I've got A to A. And B goes to B. And B also goes to D. And see, that's not going to be the identity. And then I got D goes to 3, but then goes to B. And also to D. Okay, and of course C's didn't get anything. Okay, so a couple things mess this up, right? We instead of getting A, B, C, A, C, C, B, B, D, D, whatever. The fact that this goes to 2 different things kind of messes us up, and the fact that we don't ever hook this C up to anything causes trouble. So I'm calling that investigated. That's just a good observation that unless we're dealing with relations that are functions, and those functions have certain properties, 1-to-1 and onto, then the inverses won't play that magical game that we want them to play. Okay? And that's it. We're going to do 17, I think. Let me make sure that's it. Yep. We'll start with 17 in class and then move on to other things in 6.1. So enjoy, and I will see you later.